2026 conference that will be held here in Nairobi, Kenya. And this will be the 13th conference of AMRS. And we have organized a pre-conference, which will start on 5th to 6th December, followed by the main conference, which will be from 7th to 10th December at University of Nairobi here in Kenya. And our main theme is material science and innovation, that is driving sustainability development and social economic transformation in Africa. And we have quite a number of themes that are materials engineered. So the first one is the biomaterials and materials for health. We have materials for agriculture, materials for energy, materials in construction, building infrastructure and nanotechnology. And we also have materials for environment, water and sanitation, materials in mining and mineral processing. Then we also have a theme on advanced materials, which cuts across new devices, quantum materials, optoelectronic materials. We also have materials of manufacturing of materials and structures. And one of the main themes that we have, and which is also the discussion for in our today's meetings, artificial intelligence in material science. But we shall also have quite a number of special sessions. The first one being a MLS Symposium. We have a session on phosphorus, we have a session on African light source, and many others that will come in play. So this event will take place in December 2026. So kindly mark the dates. Thank
Okay, thank you very much, Dr. Odari. I'll take this opportunity, I think, just to welcome everyone and just maybe in 1 or 2 lines to just give a brief introduction of what the African MRS is all about. So basically, we're a Pan-African organization where our main objective is to promote excellence in all aspects of materials research, where we create a platform for networking, where we try to ensure that all the 55 countries in Africa, they work together, we get to know one another in terms of material research, and also to connect Africa to the rest of the world. So we have been having the headquarters at Bitri in Botswana from 2017. And in 2021, we also became the first ever regional office in Africa for the International Union of Material Research Societies. So I think our work has gone beyond just Africa, but we are very much present on the global stage. And we are very grateful to the government of Botswana and the Botswana Institute for Technology Research and Innovation for giving us financial and infrastructural support from the inception. So we are very grateful for that. With those few words, I would like to now hand over to Dr. Maseka, who is the lead researcher, nanomaterials at the Botswana Institute for Technology Research and Innovation, who is going to introduce our guest speaker. Over to you, Dr. Maseka.
Thank you, Samuel, Dr. Chigome. It gives me great pleasure to introduce Professor Takao Someya, who's going to be giving a talk today. He's a professor at the University of Tokyo, and he's going to be giving us a talk on electronic skins for robotics and wearables. Prof. Someya is an executive director and vice president and professor at the University of Tokyo. He also serves as director general of the Division of University Corporate Relations with oversight of startup initiatives. He's recognized as an inventor of electronic skins, which was featured in Time magazine as one of the best inventions of the year in 2005. His current research focuses on next-generation wearables with organic electronics for applications to healthcare, biomedical, and robotics. He has also held distinguished appointments, including Global Scholar at Princeton University, Global Foundry Visiting Professor at the National University of Singapore, and Hans Fisher Senior Fellowship. So with those welcome remarks, I'd like to introduce Professor Takao Someya.
Okay, so yeah, can you hear my voice?
Yes.
Yes, it's loud and clear.
Okay, so thank you very much for your kind introduction. And my name is Takao Someya from University of Tokyo. So I'm so excited today to share with you the latest progress of stretchable, flexible electronics with material community in African continent. So, and also I'm immediately past president of Material Research Society in the US, and happy to make a stronger connection with African MRS and also International Union of Material Research Societies. So this is my first presentation at the African Joint Webinar. So thereby, I want to spend the few minutes to introduce myself and to introduce the University of Tokyo, which is my home institution. The University of Tokyo was established in 1877. So we have a long history and a strong academic foundation. Our institution is composed of 10 undergraduate faculties, 15 graduate schools, and 11 research institutions. So we have over 29,000 students and more than 11,000 staff. So we are proud of growing connection with the Africa. We have had the honor of hosting distinguished guests. The president of African Development Bank, Dr. Adesina, visited our university and gave a special lecture to our students. So we held a joint session in 2022 with Excellency Mokgweetsi Masisi, the president of Republic of Botswana. And also we organized the student seminar co-hosted the UNDP and student of University of Tokyo. So we are committed to welcoming outstanding students from Africa. We have currently 28 students from African continent. They come from many different countries. We also host events to host a community such as the U-Tokyo African Evening, where many leaders in industry and international organizations joined together with a student from Africa. And you may see, so here is the president of University of Tokyo, Dr. Fuji, and we could see many leaders from international organization. And the University of Tokyo is actively supporting the startup creation through our quite aggressive plan to increase the number of startups by factor of 10 in the following 10 years. As of March 31, 2025, the number of U-Tokyo related startup company has reached 638. And 33 companies reached IPO and 74 companies M&A. So success ratio it's not so bad in comparison with the global top universities. So our approach focuses on 3 key areas. One is the globalization. Particularly, we are emphasizing the collaboration of Global South, including Africa, and also strengthening deep tech. And social entrepreneurship training play a very important role in our educational program. And we have several educational programs that exemplify our engagement with African countries. For example, we held the Africa Entrepreneurship Workshop in October 2024, where the capitalists, very famous capitalists, are invited from the Africa. And also in partnership with UNIDO, we have the Africa Youth Entrepreneurship Program, through which 10 of our students visited startup companies in Kenya in the last year. We also ran the U-Tokyo JICA International Cooperation Pilot Program. In March 2025, 8 of our students participated in a 2-week educational project in Ghana. So to select the 8 of our students, can you imagine how many students applied this program? Actually, we received the over 100 applications. And finally, we selected the 8. So this program was so popular. And this program provided a stimulated experience of international cooperation activities. Through this, students gain a deeper understanding of the reality and the challenges in Africa, and developed practical skills and built the global and local network. And looking to the future, we are planning to initiate the student exchange program with several universities in Africa. So one of the program partners is Stellenbosch University and also Addis Ababa University. So where the MOU signing was planned this summer. And at the University of Tokyo, we believe in the power of social entrepreneurship to address the key challenges facing Africa. We are exploring how key technology like artificial intelligence, sensing, and drone can be applied to these problems. In doing so, we consider 3 key perspectives, namely economic value, sustainability, and social problem solving. So in that way, we believe that the combination of social challenges, key technology, key perspective may provide the abundant opportunities for young people. So this is the quick introduction of the activity at the University of Tokyo, and then going to move my own research. So this is the outline of my presentation. So after brief introduction, I will first talk about the ultra-thin organic electronics with an emphasis for the wearable tech. And then going to be nanomesh electrode that can be directly attached on the surface of skin with minimizing the risk of inflammatory issues. And then quickly touch the smart wears with utilizing the stretchable sensors, and quickly summarize my talk. So I always begin my stories with showing the photo of electronic skin. So you may not be familiar with the electronic skin. So what is the electronic skin? That is truly animal-like stretchable sensors that can detect the temperature and pressure distribution simultaneously. So most of the mainstream silicon-based technology is rigid, and that cannot be applied onto three-dimensionally curved surface. But by utilizing the material softness of organic electronics, we try to introduce the skin sensitivity to the robot. So our technology was featured by Time magazine as one of the best invention of the year in 2005 and appeared part of the cover illustration. So we are dreaming the situation. So if robot with sensitive skin will feel and even respond to a person's warmth while shaking hands, consequently letting people feel that robots are warmer. So do you know what I mean? Robot is recognized as a cold steel object, but if the robot body is covered by sensitive skin entirely, people may start feeling robots are getting warmer. So there is no scientific evidence, but we try to prove this concept with establishing the large area electronic skin for robot. So this movie shows you the manufacturing line to fabricate the thin film transistor active matrix for sense application. And one of the uniqueness of this manufacturing system is TFT could be manufactured by all printing process that may include the inkjet, gravure, screen, and others. So thin film plastic foil is temporarily supported by the glass substrate and yield to the all the fabrication with printing. And this movie shows you how our device works. And it doesn't look like flexible devices, but those kind of high resolution active matrix is usually manufactured on glass substrate, but glass is fragile. So jumping should cause the device failure. But because our device is manufactured on plastic film, it exhibits the amazing durability with maintaining the high spatial resolution and also high data readout. So immediately after fabricating the first generation of flexible robot skin, we instantly recognize how important to introduce the mechanical stretchability to integrated circuit. Indeed, without stretchability, we cannot apply the e-skin onto a movable part like joint of arms, and it is impossible to put the e-skins onto three-dimensionally curved surface like robot face. But how we can make the stretchable integrated circuit? Our approach is quite straightforward. First, we put the two-dimensional array of rigid islands that are embedded in the rubber substrate. And then we can print the organic transistors at the exact position of rigid island. And finally, source drain and other electrodes are connected by using an elastic conductor. So in that way, when we stretch our devices, so all the strain are accommodated with changing the length of wires. Thereby, we succeeded in achieving the stretchability over 145% without causing any degradation. So one of the uniqueness of our research was the development of novel elastic conductors. So you may see the elastic conductor that's connected to the light emitting diode together with a battery, transmit the sufficient electricity to obtain the bright light emission. So our printable elastic conductor achieved the high conductivity close to the 1000 Gmens per centimeter and stretchability over 400% simultaneously. So you may see even though we stretch our material substantially, the brightness or light intensity didn't change at all. This means even though we stretch our device substantially, the change of resistivity could be suppressed. So in that way, we can utilize the elastic conductor to make the stretchable integrated circuit. So this view graph shows you the ink formulation. So we add the silver flake with a typical dimension of 2 to 3 micron among the fluorinated copolymer with adding the surfactant and organic solvent and mixing together and print once and annealed at 150 degrees Celsius. So when we observe the cross-section of printed elastic conductor, we eventually realize the silver nanoparticles are naturally formed and uniformly and densely dispersed among the rubber matrix. Although we didn't add the silver nanoparticle intentionally. So as I mentioned, we simply utilize the silver flake with 2 to 3 micron, but silver nanoparticle is naturally formed. And you may see this is a magic of nanotechnology that allowed us to obtain the high conductivity and high stretchability simultaneously because of the efficient percolation conduction. And then I move to the next topics, that is conformable sensors. So this slide shows you a very famous development reported by Professor John Rogers, Northwestern University. So Professor Rogers and his co-worker reduced the silicon tip down to a few micron that is temporarily supported by the ultra-thin plastic foil, and then applied the surface of a human body directly. So they call this technique the epidermal electronics or electronic temporal tattoo. With establishing the physical and intimate contact, the group succeeded in improving the signal-to-noise ratio to detect the electrophysiological signal like EEG or EMG or ECG. So next slide shows you the video of world's thinnest and lightest organic thin film transistors. So he's Dr. Martin Carton-Brunner, who was my former postdoc, and throw away the ultra thin film devices from the 5th floor together with the bird feather. So it's lighter than feather and floating in the air. And even though that reached to the ground, the device didn't break at all. We utilize the ultra thin film with a thickness of 1 micron, that is factor of 10, thin as a kitchen wrap. And after fabrication, we delaminated from the supporting substrate. So because of the thin film feature, it exhibits the amazing conformability. And crumpling doesn't cause any mechanical failure. So we utilize the 1 micron thick PET film, commercially available with reasonable price. And after fabrication, we prepare the pre-stretching rubber, laminated together, and to transform the wrinkling structure on the surface, like accordion structure. So in that way, ultra thin film devices could be transformed to be stretchable devices very easily. And one of the good examples to achieve the integration of multiple electronic function is ultra-thin pulse oximeter. where the red pellet, green pellet are integrated with organic photodetectors. So thin film may be wrapped around the fingertip with establishing the intimate and conformal physical contact on skin, and start monitoring the blood oxygen level with high precision. And photonics based on organic semiconductor is so fascinating. And another example utilizing organic semiconductor is ultra-thin organic solar cells. So power source is always needed to supply electricity to the wearable tech. The organic photovoltaic cell is one of the promising candidates to supply electricity to the on-skin sensors. For that reason, our research group are intensively working on the fabrication of organic solar cells on ultra-thin film. So this is the efficiency as a function of the year. The dark black dot is OPV, manufactured on rigid substrate, and blue squares is efficiency of OPV manufactured on plastic foil with a thickness larger than 10 micron. And red data is the ultra-thin film with a substrate thickness less than 10 micron. You may see the reduction in substrate thickness make it difficult to achieve the higher efficiency. Why? There exist two reasons. Because the ultra-thin film is easily get damaged by plasma process like high energy process. Thereby, we need to reduce the process to utilize the high energy process. And another difficulties may come from the process temperature. Ultra-thin film is easy to shrink with elevating temperature. So we have to reduce the process temperature, ideally at room temperature. And thanks to recent intensive effort, we can achieve the fairly high efficiency on ultra-thin film with a thickness of 1 micron. And one of the good value in our group is 17.7%. And also, we are going to increase the effective detection area to get the large total amount of output power. So currently, we are making the effective area of 10 square centimeters with the efficiency over 13%. And then we obtained the total output power of 130 milliwatt. So this is sufficiently high to supply the electricity to the wireless, low power wireless module. And then I want to tell you the recent progress of system level integration with utilizing the OLED, OPV, and also organic photo detectors. So even though individual devices could be manufactured on ultra-thin film, but laminate together and the total thickness may increase, but the thickness may be usually dominated by the thickness of glue or double scotch tape to maintain the total thickness to be super thin. So ideally, we want to laminate the individual film without using any glue. To achieve our goal, here is a new technique. That is water vapor plasma assisted bonding. So when gold film are deposited on 1 micron thick polyethylene and yield to the water vapor plasma to introduce the OH group on the surface and laminate it together. So And then eventually we realize the gold could be bonded, and also pyrene could be bonded. We don't see any vacancy, and we get the tight connection. So in that way, we succeeded in laminating ultra-thin film without adding any glue to maintain the total thickness to be super thin. And also to make the different types of organic photonic devices, we developed the very simple 3-layered structure adapted. So our structure can be seen here. So here is the substrate and transporting layer, active layer, and transparent electrode. So such a simple 3-layered structure, we could make the OPV, OPD, and OLED, and integrate it together. So one of the good examples to realize the integration is self-powered, free solution processed PPG sensors. The PPG sensor module is placed on the fingertip with establishing the good intimate physical contact and start monitoring PPG over 1 month. So such a free solution process could realize the, minimizing the material wastage, and that is ecologically friendly. And then I'm going to talk about the next topics, which means the nanomesh electrode. So although the ultra-thin film electronics is so fascinating, however, there exists the one serious problem. That is gas permeability. So when the ultra-thin film directly attached on the human skin for a longer period of time, that frequently cause the skin problem, redness, itchiness, and irritation. So to solve that, so we developed the breathable nanomesh electrode. It firmly adheres to the shape of the skin. It is ultra thin and lightweight, and there is no sense of fit. So let me show you one video describing our recent progress. That may take the 1 minute.
I'm Takao Someya, a professor at the University of Tokyo. Our on-skin sensor utilizing nanomesh electrode is ultra-thin, lightweight, stretchable, and breathable. It is capable of monitoring health conditions simply by pasting it onto the skin. New sensor can be worn on the skin continuously for a week without causing any inflammatory issues. Our skin display is a 24x16 array of micro LEDs, and it exhibits simple graphic with motion because it is made from thin and soft materials. It can be freely deformed. The skin display also showed an electrocardiogram measured by using nanomesh electrodes. Combined with a wireless communication module, the acquired biometric data can be transferred to a medical cloud, and your home doctor can monitor your health conditions while you stay at home. In the future, we envision human-friendly skin electronics that will lead to improving the quality of human life.
So I hope that you like this video, and we filming the devices manufactured in our research group. And this slide shows you the fabrication process of nanomesh electrode. First, nanomesh is made of polyvinyl alcohol which is known as a water-soluble polymer by an electrospinning method. And then gold patterns are formed by vacuum evaporation through a shadow mask. And the nanomesh electrodes are laminated on the surface of skin with adding some water by spraying. So PVA is dissolved into water and washed away completely. Finally, porous gold thin film remained on the surface of skin. So this is the nanomesh electrode attached on the fingertip. The shining part is a nanomesh, and non-shining part is bare skin. So that used to be covered by the PVA, but that could be washed away completely, thereby this is bare skin. And the shining gold part looks like a continuous film, but if we look at the nanomesh layer by SEM, obviously that exhibits the porous structure. And also this is magnified photograph, and again shining part is nanomesh, and non-shining part is bare skin, and dark spots are sweat pores. And if you look at the sweat pore region, both on gold region and also non-covered region carefully, we observe the same amount of sweat are penetrating from the sweat pores. So this means that the natural penetration of sweat and the natural vaporization of sweat are not prevented because of the breathability. So such a gas permeability is very important to ensure the biocompatibility. So when the nanomesh conductors are put onto the people's forearm continuously for a week, and none of the patients exhibit the doubtful inflammatory issues. In sharp comparison, the continuous film means 1 micron thick pyridine or 1 millimeter thick silicone. Both of them are known as a biocompatible material, yet the lacking of breathability then exhibits the fairly high risk of inflammatory issues. And recently, we improved the durability of nanomesh. Simultaneously, we developed the Janus membrane that utilizes as a pump to remove the penetrating sweat immediately. Our Janus membrane-based skin electrode exhibits the amazing stability, and we succeeded in monitoring the ECG signal continuously over 6 days without degrading the signal to noise ratio. And then I'd like to spend the few more minutes to describe the smart wears. So stretchable sensors may be laminated on the surface of sports wears to make the smart apparel. So one of the good example is motion capturing system. So here the 7 accelerometer are embedded on the surface of sports wears. And by utilizing the AI analysis, we can monitor the user's motion with high precision. So this is motion capturing system. In conventional motion capturing system, we required the multiple camera setting, and the user may need the markers on the joint on part. But in our new development, just user wear the smart wears, and after calibration that takes the few seconds, the system can monitor the user's motion with high precision in real time. Because we don't require the multiple camera setting, so we can monitor the user's motion anywhere anytime, even outside. For example, during the marathon or during playing the golf. And one of the tangible application is sports application. So she is Miss Umehara, a member of national taekwondo team in Japan. And during the corona pandemic, Miss Umehara found difficulties to meet her coach in person. And then we sent our devices to a gym, and then she wear our devices, start monitoring her motion with high precision. So data could be sent to her coach wirelessly, and finally, she obtains the feedback from her coach remotely. And another example is the remote rehabilitation. Person with spinal cord injury participated in rehabilitation session at home with wearing our prototype and communicated with his physical therapist remotely. So such kind of remote rehabilitation or remote medicine are getting more and more important. And somehow the development is being accelerated by corona pandemic. And here, I want to show you the quite exciting latest progress. So this is the 3D ECG smart wears. So left photo shows the conventional Holter ECG, where the multiple electrodes are placed at the appropriate part of the body and connected to the recorders by using external cables. But in case of new development, the position of electrode are precisely determined and embedded from the beginning. And just the T-shirts, smart T-shirts was shipped to the patient house by regular mail, and the patient just wear this T-shirt and start monitoring 3D ECG with high precision. So in that way, the one of the startup company originated from our invention could achieve the world first made inspection of 3D ECG. So that smart T-shirts may contain the multiple electronic functions like controller, power supply, wireless module, and processor and memory. And also that may start monitoring the ECG, body temperature, and user's motion. So in that sense, this is sort of a smartphone, wearing smartphone to monitor the person's health condition with high precision. So when I show our concept of smart wears, I frequently ask this question: what is the main difference between smartwatch and also smart wears? So here is my answer. Smartwatch is so fascinating, and many people start using smartwatch. However, it is unlikely that the position of wrist may start monitoring the person's health conditions entirely. So if you had a stomach problem, we want to put the sensor in your stomach. So in that way, monitoring full body by using the smart wears may be the key to get the much more vital signs from the entire body. And this slide shows you the quick development history in the past of my research group. So our research group has developed the robot skin, making the multi-point, multi-modal, large area sensor. But skin needs the stretchability, and we have made the world first stretchable integrated circuit. And also we reduced the total thickness down to 1 micron to achieve the better conformability. At that point, we expand our target object from robot body to the human body, start monitoring the vital sign with high precision. But long-term health monitoring requires the biocompatibility, and then breathability is quite important. So before concluding my talk, I'd like to acknowledge my collaborators. So this is my this is a photo of my research group, and Dr. Yokota and Sunfun Lee has made the ultra-thin devices and nanomesh electrode, and organic photovoltaic cell was developed by Dr. Fukuda and his team members. And in summary and conclusion, today I talk about the recent progress of electronic skin, and by utilizing the soft materials that may harmonize with biology or human. So we expect to create the new application in the field of healthcare, biomedical welfare, sports fitness, AR, VR, entertainment, and even more. So thank you very much for your kind attention.
Thank you so much, Professor Takao, for this informative and very educative talk that we've had. Believe most of us are very keen. And I would like to welcome a few questions from our participants who pose a question. And I come from the field of perovskite materials research, where humidity is a major hindrance. And here we are discussing about water vapor plasma assisted lamination. What is the secret behind using water in organic photovoltaics or in organic materials? Maybe we can employ that in perovskites.
Okay, so thank you very much for your question. So here I utilize the water vapor plasma to introduce the surface of to introduce OH group on the surface of gold and also parylene. So we didn't expose the active layer of organic semiconductor to the water vapor plasma. So that means to utilize the water vapor plasma, the organic devices have to be covered by encapsulation layer. So this might be the important point. Is that the answer to your question?
That one answers my question. Thank you for clearly answering that. Now, participants, if you have a question, please raise your hand. Then, if you have a question, kindly raise your hand. Maybe as you wait for more questions, how do these devices, how effective are they based on our different levels of sweating? These were not even wearable, the ones that you apply directly on the skin. how effective are they with reference to sweat?
Okay. Sweat is always a big problem for the monitoring of health condition for a longer period of time. So because the if sweat may be accumulated between skin and devices, that may frequently cause the skin issue. And also, accumulation of sweat may cause the device degradation because in any cases, it is difficult to achieve the perfect encapsulation of flexible devices. So if device is manufactured on glass and covered by the glass substrate, so that may achieve the perfect gas barrier layer. But flexible devices is made of soft material, thereby it is not so trivial to prevent the penetration of moisture, water, sweat, or whatever. So today, I didn't find the sufficient time to describe our recent progress, but we utilize the Janus membrane that consists of a hydrophilic nanomesh and a hydrophobic nanomesh layer that may laminate it together. So such double-layered structure works as a pump of sweat. So immediately the hydrophobic layer may attach on the skin. So that may remove the sweat from hydrophilic layer to the hydrophobic layer. So in that way, we could avoid the accumulation of sweat near skin. So in that way, we succeeded in monitoring of ECG over 1 week without causing the any significant degradation of signal quality. But I would say there exists much more room for further improvement to ensure the reliable long-term health monitoring.
Thank you. We have a question of someone is asking for comments. We have Neil Coville who is asking, what are the current costs and maybe future costs of these devices you're coming up with?
Cost is also quite important topics for industrialization. So today I talk about a bunch of different types of devices, but I would say nanomesh itself shouldn't be too expensive, and also that should work as the disposable devices. And today I talk about the nanomesh based on gold layer. So gold is obviously expensive, but similar signal quality can be achieved by replacing gold with silver. And then we could reduce the material cost by a factor of 20 or even more. And also we are trying to replace the silver with carbon-based material due to a cost reduction and also to improve the biocompatibility. I would say the cost is surely main concern for industrialization, but there are many opportunities for material scientists to reduce the material cost or manufacturing cost with maintaining the high precision of signal quality. And also today, I also talk about the organic thin film devices. So semiconductor devices shouldn't be too cheap, but that means so we need to use semiconductor devices for multiple times. So I would say we need to find out the engineering solution to combine the fairly expensive module that can be used multiple times and also disposable cheap cheap component, and then to find out the reasonable practical solutions.
Thank you for that.
Yeah.
We also have a question.
I have a question.
from,
I'm not able to raise my hand this side, sir. Okay.
Please go ahead. Please go ahead, Robert.
Oh, okay. Thank you very much. My apologies again for not being able to raise my hand, but I must admit this was a very, very thought-provoking kind of presentation, very informative, and I honestly want to appreciate Prof for sharing such. Thank you very much.
Thank you.
And I just have two questions. Well, one of them was partially answered when you talked about the water vapor assisted bonding, which was one of the questions. But now the questions that I have to do with the applications of this ultra thin structures. One of them is you mentioned one application in terms of rehabilitation, and we have in Botswana, we have been battling with coming up with measuring devices for assisting stroke patients in terms of gait analysis. Is this some kind of a device that can be perhaps used for measuring maybe force, pressure, incorporated into the devices we are developing for gait analysis in stroke patients?
Doc.
I think our research group focusing on the development of physical sensor. Particularly today, I talk about the electrode to monitor the electrophysiological signal and also photonic system. But our research group has already developed the flexible temperature sensor, pressure sensor, strain sensor, and also other research group are working on the development of chemical sensors. I think depend on the target application. So we need to combine the some of the flexible sensors. But as you mentioned, the target application is quite important, so that have to be specified before we start optimizing the device structure. But there are tremendous opportunities to improve the performance of flexible sensors in the future.
Thank you very much.
Okay, let's take two more questions, then wind up. And the first one is on the chat. That is from Najes Ben Ibrahim, who is inquiring whether you also work with the 2D materials in your system. I think by system it refers to coming up with electronic skins. Are they 2D materials?
Yes, 2D materials are also a fascinating solution to introduce the abundant functions to the stretchable flexible devices. So indeed, so we frequently use the 2D material to make the organic photonic system. Also, we set the organic devices because the active layer rely on organic material. But some part, like the electron transporting layer or others, may rely on the 2D materials. And also, the organic semiconductor could be replaced by 2D material to improve the mechanical durability and also to improve the electronic performance. Again, our research group are working on the organic, but that shouldn't be limited to the organic. And the appropriate combination of good materials will further improve the device performance.
Okay, maybe the last question. Let me pick one from the public chat. And this one is basically what most of us would want, collaboration and linkages. So we have a question from Nanso Okoli, who is asking for opportunities in your laboratory, more so on perovskite solar cell. But I would also like you to answer that question in general, because most of us, including myself, have interests of collaborating with such a vibrant team like you. So what are the opportunities you have for us in Africa in University of Tokyo? Thank you.
Okay, so thank you very much. We started talking with a couple of universities regarding the student exchange program, and also my responsibility at the University of Tokyo is innovation and also supporting startup. Thereby, I tend to focus on the creation of startup, but of course, pure research collaboration are welcome. And also, we are working on organic material, but we are open to work with the other material to achieve the more advanced functions. Like perovskite is also quite fascinating. 2D material is quite fascinating. And oxide or carbon, nanocarbon. So any kind of materials are welcome to introduce the more advanced functions into our stretchable integrated circuit in the future.
Thank you. We are now 4 minutes past time. I wish to know if we have any AMRS board member here with us. Maybe Dr. Chigome, you can pick from there.
Yeah, it looks like they couldn't join. I think on behalf of the African Emirates Board, I just want to take this opportunity to thank Professor Someya for the wonderful talk. I think you saw from the way people were responding that if only we had more time, I think we would have engaged for a longer time, but we know that it's quite late for you on your side. So we want to release you. And I would also want to thank, I think, everyone who joined. We're going to be having these webinars every month. And I think for those who need further information, I've just posted our website so at least you can get more information about what we are trying to do as a society. And also the recording for Professor Someya's talk is also going to be on the website so that you can be able to go through it. And where there is interest in connecting with Professor Someya, you can send an email to us. We can facilitate the communication going forward, even beyond this talk. So I think with those few words, I would like to thank everyone. And I think over to you, Dr. Odari. Thank you very much.
Thank you so much, Dr. Chigome. And once again, I want to thank Professor Takao for the nice presentation, for the very interesting presentation that you had. And we shall be, as Dr. Chigome said, we shall be having these webinars monthly, most likely at the end of every month, every last Tuesday of the month at the same time. So please, we look forward to have you in our next meeting. And again, we wish to still remind you that we shall be hosting the AMRS 2026 here in Kenya, Nairobi, Kenya, in December 2026. So we will give more information with time. And I want to thank all the members who participated. And with that, we can call it off. Thank you, Professor Takao. Hope to see you again. Pass our regards to your team, your group members. Thank you.
Yeah, thank you very much. So
Okay.
see you next time. Goodbye.
Okay, bye-bye. All right, bye.
Bye.